Hi there, we're looking today at the dot product again. We saw this last time, just saw my pen out there, saw this last time where we learned that the dot product in further maths we defined to be a dot b is the magnitude of one vector, the magnitude of the other vector, times by the cos of the angle in between. And this formula can be used quite a lot to find the angle between two vectors. We also found out if a dot b was equal to 0, that told us they were perpendicular. So if you get a dot b equals 0, it's perpendicular. And on that basis, we can do quite a lot of maths. And we're going to use this in questions regarding lines. And we saw in the last lesson that if you get a line, for instance, here is one line, and it's r equals -3, 3 minus 1, plus lambda 1 minus 3, 2. We saw that we use the direction vectors of the line to find angles between two lines. And we're going to use something similar to that today. Started anyway, explain how you can show whether or not these pairs of lines are perpendicular. Well, let's just quickly remind you what I said just now. A dot b equals 0. That's what we're after. So if you can have a look at question A for me and then question B and see if you can in your mind justify why these two vectors are perpendicular to each other, if they are, and whether these two are perpendicular to each other. So pause the video and then I'll show you what I think. Okay, hopefully you've done that. Look, I did mention before you have to use the direction vectors. These are these. So if I was doing this, I'd say d1.d2, and I'd just use my rule that -2 times 4 is -8, and then I add the answer to 5 times by 1, which is 5. Then this is -3. Now because it's not 0, so I'm going to write not equal to 0, therefore not perpendicular. Those two lines are not perpendicular. They do not cross. What angle they cross at, I don't care. It doesn't ask me to find out, so I don't care. But these might be, I don't know. So again, I'm going to do d1.d2. First line is 3, 1 there. So again, I'm using this direction vector. So if I do 3 times 2, I get 6. 1 times 2 is 2, so I'm plus 2, plus, what do we get? -4 times 2 is -8. Now look, that is 0. And therefore they are perpendicular. Okay, that's what you were meant to do. So hopefully you did that. Point perpendicular to line. Now this is a result of what we saw last time in terms of the dot product, but it's quite tricky, so you will need to take good notes. Make sure you take good notes. So there are two problems that we are often asked to do regarding whether or not a point and a line, they're perpendicular to each other. The first type is basically requires us to find a point on a line which is perpendicular to the origin. So if imagine they've got the origin, imagine you've got a line passing by. It doesn't go through it, it misses it. But somewhere along this line there is a point which we're calling P, which if you drew a line from O to P and you looked at the line, there would be a right angle between these two things. That's what we're after. And notice I've quoted that the line is written, in my example at least, as r equals a plus td. Remember, a is a point on the line, doesn't matter where it is, it's over here somewhere. And d is the direction of the line. That's my direction of the line. And that's what I'm after really. I suppose I want that direction of the line. That's still the direction of the line there. So what, to be perpendicular, that direction of the line and this point on the line from O, this line here if you like, also needs. So this has got a direction in its own, and this OP vector and the D have to be at right angles to each other. So that's the basic idea. We find OP and then we find the direction vector for the given line, and then when we've done that we can use the scalar product. Because we know they're perpendicular, they must be equal to 0. So this can also be asked, just worded differently. It might not say find the point which is perpendicular. Very often it says find the point which is closest to O. And it might seem obvious to you, it might not, I don't know. I reckon P is at its closest it ever could be. If P was there, I reckon that distance would be longer. If P was there, I reckon that distance would be definitely longer. The point P at when it's at right angles is as close as it possibly can be. OP is at its shortest. So here's an exam question. It says relative to the origin, the point A and B have position vectors that. So I'm just going to write that out. OA is 3, 2, 3, and OB is 1, 3, 4. Okay. So if I just drew a picture, I know it's very hard to do this. Find a vector equation of the line passing through A and B. Oh, that's relatively straightforward. R equals any point on the line, might as well be the A, 3, 2, 3, plus lambda times by the direction vector. So for that, I'm going to need the direction vector. And I'm just going to write direction vector and just do one of them minus the other one. I'm going to do 1 minus the 3. That's minus 2. 3 minus the 2. That's 1. 4 take away 3, that's 1. There's my direction vector. So therefore my R, for my, this is the way we write equations of lines, is 3, 2, 3 plus lambda minus 2, 1, 1. That is part A done. Okay, I like that. Part B, what's it say? Find the position vector of P on AB such that OP is perpendicular to AB. Now this is what I was just about to draw. This is my line. This is R equals this. It's my line. And somewhere on that line there is a point which is as close as I can get to the point O, and the idea is it's perpendicular, it's there. You can see that's my point P, and I can find OP relatively easy. I can find my direction relatively easy. Well, my direction vector is already done. My direction vector is this thing here. The hard thing actually is the direction, this vector at OP. So if I find OP now, the reason why it's hard is because it's a point on the line. And it's a bit weird, this. It starts at O, so that makes it easy. Going from O means you don't need to worry about where it goes from, you just need to almost know its coordinate. And its coordinate is simply, comes from this equation up here. Any point on this line, which P is, has this as a coordinate almost, it's or position vector, 3 minus 2 lambda. Notice I've just done 3 minus the 2 lambda. 2 plus a lambda, and 3 plus a lambda. Now that, I think, is a bit weird until you've done it a few times. And once you've done it a few times, you think, well, actually, these are all the same. So now I've got my OP. I've also got my direction vector. I can dot them. So if I do D dot OP, answer must be 0. So let's see what we get. If I, well, I put it in a bracket. Well, I will put it in a bracket just to highlight. Minus 2, 1, 1 is going to be dotted with 3 minus 2 lambda, 2 plus lambda, and 3 plus lambda. And remember, when I dot them, I just add the results. So minus 2 times this gives me minus 6 plus 4 lambda. Plus 1 times 2 plus lambda is 2 plus lambda. Plus 1 times 3 plus lambda, that's 3 plus lambda. Remember what I said this is. If this is perpendicular, it has to equal 0. So how many lambdas have I got? I've got 6 lambdas. Minus 6 plus 2 is minus 4 plus 3 is minus 1, which I move over to get 1. So I think lambda is a 6th. That's lambda. So what's my position vector of P? Therefore, OP equals, remember the equation. It's here, 3 minus 2 lambda. I could use either this equation or this one. OP is 3 minus 2 sixths. 2 plus a sixth. And 3 plus a sixth. It's not very nice, I agree. 2 sixths is like a third. That's like 2 and 2/3, which sounds to me like 8/3. This is like 12, 13 over 6. And I think 19 over 6. I don't think they're very nice, but I think that's probably what it says on your calculator. 8/3, 13, yes it is. Next question. The equation of a straight line, again, notice as soon as I see this, I think D. What's D? What's D? And it's minus, it's 1, minus 1, 0. That's my direction vector. O is the origin. Find the position vector of the point P on L such that OP is perpendicular to L. So it's a very similar question. We've got this line, we've got some point that we're trying to find relative to the origin over here. I know my direction vector already. I need my vector OP, and to find OP I use this equation effectively gives me OP all the time. OP is a point on the line, and therefore it is, and all you do is you go 1 plus t. You do nothing minus t. And you just, oh, last one's just 2. So now remember what I do. I say OP dot the d has got to equal 0. So let's dot them. It doesn't matter which way around you do those. I think I might have done it the other way around last time. Dot 1 minus 1, 0. That's got to equal 0. So let's do it. That's 1 plus t when I times them, plus t when I times them, plus, oh, plus nothing, equals 0 then. So I think 2t plus the 1, so I'm going to move the 1 over the other side, is minus 1. T is minus a half. That's what I think the answer is. It says then a point Q is on L. Right, then. It's on here somewhere. There you go, there. That's what I'm saying Q is on L such that the length OQ, which I draw in a different place now, there's OQ, is 3. Oh, right. Let's get rid of that there and write OP there. This length OQ is 3. Find 2 possible position vectors of Q. Again, it's not easy. These are definitely the harder ones. But one thing you'll notice is I definitely would get a little right angle triangle here. I know that. And I suppose I could find OQ. So I could say, in actual fact, I'm not even sure I need to worry about the fact this is a right angle. I think I can just use the distance OQ. Let's find the distance OQ. This is for part 2. So OQ, of course, would be a bit of Pythagoras. You'd say it's one coordinate minus the other one. And weirdly, OP has this coordinate, but so is OQ. I can say OQ is that as well. It's for a different value of t. It's just a point on the line. Now, if I use that as OQ now, and I start at this point, again, the distance from there to there, I can just use these numbers here, because here, this coordinate, of course, is 0, 0, 0. So the distance is 1 plus t minus 0, minus t minus 0, 2 minus 0. So when I do my Pythagoras and I square all those things, it's 1 plus t squared plus minus t squared plus 2 squared. And it tells me OQ is equal to 3. So that distance has got to equal 3. Now, I don't like square roots, so I'm going to move that onto the other side, and straight away that equals 9. But now I can multiply out my brackets. I can say, well, that's 1 plus 2t plus t squared. Plus, well, that's t squared. And that's 4. So I'm getting the quadratic equation here. I've got 2t squared. That's those two gone. Plus 2t plus 5 equals 9. And of course, I've got to make it equal 0. So let's do 2t squared plus 2t minus 4 equals 0. That's an equals, you can't see it. So I'm just going to type that into my calculator. I could factorize it. I suspect you can factorize it. I can't be bothered even to think about it. So here goes. It's a polynomial equation of degree 2. Numbers are 2, 2, and negative 4. And I get the answer 1. And what's the other answer? T is minus 2. Now, again, once you know your t values, we can now find our position vector. So we can put those values of t back into our OQ. So OQ equals, when t is 1, it's 1 plus 1, that's 2. Minus 1 and 2, that's 1. Or OQ equals, put minus 2 in, that's minus 1. 2, 2. That's what I think the answer is anyway. Let's see. Ooh, I can't really see it here. And oh, I forgot to do that for the first one. A bit naughty, but I'm sure that works. And what's that say? 2 minus 1, 2. That works. Minus 1, 2, 2. It's all underneath and all higgledy-pickledy, but it is right. And note again, I was a bit naughty. I just found t for this, and it did say find the position vector of the point P. Now, you might think, crikey, that was a lot of work. But in actual fact, there's a lot more still to do. I've got this question here, which does a similar thing. That's almost identical. And notice there's another point. We are going to then, before we finish exercise 2D, we have to do points perpendicular to the line as well, from a different point, which is not the origin. Now that's harder still. So we'll make sure we go through that in class, and that will again require more explanation. But other than that, thank you very much.